So here we are in Thermo video 5, and hopefully this is going to be a quick one if I don't ramble too much, because all we're going to do is what you see on the page right now. Talk about standard values and do examples number 8 and 9, hopefully both of which will be fairly quick. So with enthalpy, the difference in potential energy from reactants to products, we can think about thermochemical equations and stoichiometry. In the lab we'd use calorimetry. Or here, this is the way that's probably new to everyone here, which is using tables of standard values. Tables of standard values means that there's certain things that we know what their enthalpy or how much energy it takes to make them, or the heat required to make them. And what we'd be looking at is standard enthalpy of formation. So the delta H means enthalpy, that degree symbol means standard, and then the F means we're talking about formation, and that was introduced on the first page of notes. So what this means is how much energy does it take to make 1 mole of a compound from its elements. So if we're making CO2, carbon and oxygen. If we're making water, hydrogen and oxygen. Calcium carbonate, calcium, carbon, and oxygen. And these are standard or known values. And when we say standards, that degree symbol means certain things. It means that we are dealing with 1 atmosphere of pressure. We're dealing with 25 degrees Celsius, so not the exact same thing as STP, but more of the room temperature situation or standard lab conditions. And if we're dealing with solutions, they're 1 molar. The standard heat of formation is defined as 0 for an element in its standard state. And if you look at this definition, that makes sense. If I'm going to make oxygen gas from its elements, it's made of just oxygen gas. So to turn oxygen gas into oxygen gas doesn't require any energy. But if I wanted to turn oxygen gas and hydrogen gas into water, that would be a change in energy. We would have to break some bonds, which would be energy in. We would make some bonds, which would release energy. This reaction, or excuse me, this equation, not reaction right here, is given. There's actually a couple different versions of this in the thermo section where it's talking about enthalpy, entropy, and energy, but it's all the same idea. The change in energy for our reaction is the sum of the heats of formation of our products minus the sum of the heats of formation of our reactants. You would get all of these values either from a table like what we're seeing right here, or if it's for mastering chemistry for a lab for something in class, there's an appendix in the back of your book, or you can look them up online. And as we look at these values here, so we've got this, some values down here, even before we get into these exact calculations, we see all 6 of those have negative values. The values are negative because these substances are more stable when the electrons are being shared and after a bond has been formed. I don't know off the top of my head if there's any positive values. There's probably some complexes and maybe even some compounds that you are forcing together and are not very stable. They're kind of an intermediate step. But really, you're going to see mostly negative values for delta H of formation. And if you had to explain why, it'd be the forming of the bond from the separate components released the energy. So here, calculate the delta H. We've got our reaction. We're going to sum up these two. We're going to subtract from that these two. We're going to get that value. It's going to be very easy here. So it's just a matter of having enough space for me to write all of this. So my delta H is going to be the sum of the products. So the products are the 2H2O, so I have 2, and the value for H2O is negative 242. Then I add that to the 1 silicon tetrafluoride, which negative 1615. So I've got that. Those are my products. I'll slide over and do my reactants. So my reactants, there is 1 of the silicon dioxide, 911. There is 4 of the hydrofluoric acid or hydrogen fluoride gas. Then we zoom out here. We've got that all set up, and very simply we just put all the numbers together and we get the answer of negative 112 kilojoules per mole reaction. Very, very simple math. You're probably going to get 1 point for this on a free response. The challenging thing here is you could be asked to do this on a multiple choice. And when you're doing that, what you want to do is turn these into easy numbers. 2 times negative 250, negative 500, negative maybe 1500. So this is about negative 2000. Well, this is negative 1000. 4 times 250, this is negative 2000. What did I have here? I had 2000 and 2000. Those aren't great estimates because that gives me 0. So then I would need to think maybe a little bit bigger. Okay, let's see. Well, this one's 4 times 270. That's actually a little bit more than 1000. So this side is a little bit more than this side, which is how we know that it's slightly negative. But if you just rounded it like I did to 500 and 1500 and 900 and, well, 900 and 1000, you at least kind of know the magnitude of about where it's going to be. But with the mental math, you don't want to round too much because you saw that you could have actually, if you rounded it the way that I just said, the 500 and 1500 and 900 and 1000, you would actually get 100, but it would be would it be positive? No, it would have came out, it would have been negative 100, so it would have worked out in this case. But it's really easy to over-round slightly and come up with something that's not totally right. So all of that explanation was giving an example of doing what you're supposed to, but taking it too far and all of that. Basically to say, you're going to have to do this in your head. You don't need to do 2 times 242 is 484 minus this, especially if you're short on time. You need to make a best guess by rounding, but then if you have the time, come back and actually use the numbers the way that they're written is a good thing to do, to double check, because they are questions that can be solved pretty easily. So you've got all your values there. The trick that can happen with this is going to appear on the next one, so I'm not going to explain it ahead of time. We're just going to jump right in and look at that. The other way this can be asked is, instead of given all our standard values, all of our heat of formations, and ask for delta heat of reaction, we could be given the heat of reaction and ask for a standard heat of formation, and that's what it says. For a lot of substances, we can't make the compound from its elements. It just doesn't happen. You can't make the C6H12O6 glucose by taking some graphite and some hydrogen that's in the air and some oxygen in the air, and then poof, it turns into glucose. That's not the compound it would form. So we have to find out heats of reactions or heats of other reactions and use it to determine what the heat of formation would be. So find delta H of C6H12O6 from this information. The key thing that we have here, in addition to this table, is we have our heat of reaction, and we want to remind ourselves that that is exothermic, which means that's negative 2800. So as I zoom in down here, negative 2800, that's the overall delta H, equals products minus reactants. So slide over slightly here. We have 6 CO2s, and the CO2's negative 393.5, plus 6 of the H2O's, slide a little bit more there. H2O is negative 285.8, and then that is minus my reactants. So minus the thing that I want, X, which there's only one of, but then we have oxygen. So we slide over, we know we have 6 oxygens, but in my table here it only gave me CO2 and H2O, and you think, well, maybe it's up in the data above, so they didn't rewrite it and it's not there, and then you're thinking, do I have to look this up in the book? What is it? And the important thing is to remember that elements in their states, in their free uncombined state, in its standard state, have a heat of formation of 0. So to form oxygen gas from oxygen gas takes no energy. So we've got all of these. We're solving for that. It comes out to negative 1276. Hopefully you kind of trust me because I don't like doing the simple algebra, going through it step by step. If you show this work, what I have here, and then plug it into your calculator and get this, you're going to get the full points. You're going to get points if you're showing it step by step by step as well. But you definitely need to show what have you set up, and then you need to have your answer with a unit. So that's from standard values, pretty quick and easy. We've got Hess's law and bond energies left next, so we'll jump into those with videos 6 and 7.